Welcome to this first lecture in this new series of lectures in linear algebra. We will be discussing the notion of a field in this lecture, and let me delineate some prerequisites. So we need to know the language of sets, functions, relations. All of this is available in the playlist named Kickstart. And we also need to know the well-ordering principle, not for this lecture, but for the lecture series in general. Okay, and all of this is available in the playlist named Kickstart. Of course, we will be assuming high school level mathematics. And with that, let us start. So, we will be talking about rational numbers first before we get into the abstract notion of a field. So, let's recall what is this. So, this symbol stands for all rational numbers, which is those numbers which can be written in the form of p by q, where p is some integer and q is a non-zero integer. Right? These are rational numbers. Real numbers, well, not easy to describe, but we have a feeling as to what they are. Typically, we represent them as things on a line. This is the zero of the line, and then we have a nice intuitive image in our heads. But this is a sufficiently sophisticated object, and this is first introduced properly in a course in real analysis. We do not need to go there. Just our basic intuition of real numbers is sufficient for this lecture series. And then we have the complex numbers. And for this lecture series, it is just enough to know that these look like a plus ib, where a is a real number and b is a real number. And the basic, just what we learn about complex numbers in high school is what we will be assuming. That's all. Okay, so once we have that, let's just focus on rational numbers for the moment. Everything we are going to say about rational numbers is applicable to these two also. So there are some properties here. We have an operation of addition and an operation of multiplication. Addition consumes two rational numbers and produces a rational number, and same for multiplication. And there are some properties that they confirm too. So first of all, let me write a simple trivial thing, that if we have two rational numbers a and b, then if you add them, you again get a rational number, and if you multiply them, you again get a rational number. So this is clear by definition of addition and multiplication of rationals. And there are further properties. So we have the associativity law. This holds whenever a, b, c are rationals, and we similarly have the multiplicative counterpart, right? And we have commutativity for all rational numbers a and b, and same for multiplication. We have this additive identity property, that 0 plus a is a for all a, where a is again a rational number, and 1 times b is b for all rational numbers b. Okay? We have this additive inverse. So this is 0 for all rational numbers a, and this product is 1 whenever a is non-zero. If a were 0, this cannot be written. Doesn't make any sense because 1 upon 0 is not defined. And lastly, we have the distributivity property, that addition and multiplication behave well with each other. Okay? So these are some properties of rational numbers that we are familiar from high school, and the notion or the definition of an abstract field that we will come to is basically abstracting out these properties. That's all a field is doing. all of this can be written for real numbers and all of this can be written for complex numbers. So a field is basically a single, a single abstract object which is capturing precisely these properties. And hence you can, if you have some statement that is true for an abstract field, it will also hold for all of the three of these things simultaneously. And that is the power of abstraction. You are able to put a lot of things under a single umbrella and therefore do not have to labor multiple times to prove the same thing for different objects. All right, so let's now get started with the main concept. So what is a field? A field is first of all a triple, where this is just a set, this is a set, some non-empty set. This is a function from f cross f to f. Just like in rationals, what does addition do? It consumes two rationals and produces a rational. We are abstracting that out. Now, since there is no such thing as your usual addition on f is just some set. So we are saying it is equipped with some function of this sort and another function with this sort, where the symbol that we use is the same as the symbol for addition in rationals or reals or complex. We abuse this symbol, that's okay, but one should be mindful that this plus has nothing to do with the plus that we see when we are dealing with rationals. Okay? So yeah, so field is a triple where f is a non-empty set, and these are two functions which are consuming two elements of this or a pair of elements of the set f and produce an element of the set f. This is called the addition function and this is called the multiplication function. The names don't change. Okay. And also, before we write down, complete the definition, let me remark that when we, instead of writing this is the output of plus when you feed it this pair. Instead of writing that, we write that. So this is our, this is just a more convenient way of expressing this. Technically it is that, but when we write this, we just mean that. Okay? Similarly for multiplication, instead of writing this, we will just write that, or we may even write this. In fact, most of the times we will be writing this. This dot will be suppressed. Okay, so with those things out of the way, the first property this triple must satisfy, if we want to call it a field, is associativity, which says that alpha plus beta plus gamma is equal to alpha plus beta plus gamma for all alpha, beta, gamma in the field, and similarly for multiplication. Right? So this it must satisfy. This is called the associativity property. And just to be very, very clear, let us write this down in a more formal way. So this is meant to capture the following somewhat ugly looking expression. So this is that thing. First you operate the addition on this pair, and then the output you get, you operate on that pair. Right? So instead of writing that, we are just writing this, and it should be clear now why even we do this. Okay. So that's your associativity. And now we need commutativity, or rather we will define what we mean by commutativity. So it just means this happens and this happens. Again, for all alpha and beta in the set F. Okay. Additive identity and multiplicative identity. So additive identity insists that there exists, and before that, let me push it up. So here we insist that there exists some element which we will call 0. Again, this 0 has nothing to do with rational numbers. This is just a symbol that we call 0. There is an element 0 in F such that 0 plus A or 0 plus alpha is alpha for all elements of the field. And there exists an element again which we will call 1, but nothing to do with rational numbers, such that 1 dot alpha is alpha for all alpha in F. Okay. And here it is important to show that actually there is only one such element. This insists only on the existence of such an element, which is called the additive identity. So this element is called an additive identity. We haven't proven uniqueness yet. So this is called an additive identity if it satisfies this for all alpha, and this axiom insists that there is at least one additive identity in the set F. But the definition of additive identity automatically implies its uniqueness, and let me argue why. So suppose there were two different additive identities, 0 and 0 prime. So if 0 and 0 prime are additive identities, then what is 0 plus alpha? Or rather, let me say 0 plus 0 prime, because that is what I need. So 0 plus 0 prime is what? It is same as 0 prime. Because just think of 0 prime as alpha for the moment. And by the definition of additive identity, 0 plus alpha must be alpha. So 0 plus 0 prime must be 0 prime. Okay? But by commutativity, this is also same as 0 prime plus 0. And now think of this as the additive identity and this as just some element of the field. So this must be 0. And that's it. That shows that 0 prime must be equal to 0 because these three things are equal. Similarly, you can argue that the multiplicative identity is also unique. So it makes sense to say the multiplicative identity or the additive identity. Okay? Fine. Now we can talk about additive and multiplicative inverse. So this axiom insists that for all elements in F, there is some other element, beta, such that alpha plus beta is the additive identity. And this axiom also insists on the multiplicative counterpart. It says that whenever you have a non-zero element, so this additive identity is also called 0 for obvious reasons. So whenever we have a non-zero element, there is some beta such that this is equal to 1. So if you multiply, you get the multiplicative identity. Okay? Now, one thing I want to mention is that here again, we are only insisting on the existence of such a thing, but you can show similar to this kind of reasoning that actually there is only one such element. So for each alpha, there is one and only one beta which satisfies this. It will follow. So this unique beta is called the additive inverse of alpha. Right? If I'm not writing that. And the notation for this is minus alpha. That's a notation. And the notation for this guy is either you may choose to write this or you may choose to write that. Both are fine. Okay. Lastly, the distributivity property. For all alpha, beta, and gamma in the set F, we have alpha dot beta plus gamma is alpha dot beta plus alpha dot gamma, where of course I should put brackets so that there is no confusion. And that's it. So a field is a triple where plus and dot are functions of this sort which satisfy these 5 properties. These 5 properties were already there with the rational numbers, but we have just extracted that out and put as an, as a template to work with in some sense. Okay, fine. So let's look at examples of fields. Well, I'm not going to say anything very, very new. Rational numbers. So when we say rational numbers are fields, we mean rational numbers equipped with the usual addition and the usual multiplication. This is a field, this triple, because a field necessarily has to be a triple. Real numbers again form a field if you take the usual addition and usual multiplication. Complex numbers form a field if you take the usual addition and usual multiplication. And then there are these things called finite fields. We will not go into them, we will not define them, but there exist finite fields, meaning there are finite sets with field structures on them. They are very, very useful, but in this lecture series, we will not be going into them. Okay. Having said all this, a lot of the times when we are talking about a field, suppose I am to talk about a field, which is this triple, I may, by abuse of notation, just use the symbol S. And this will be clear from context. This will not cause any confusion. Okay, so this kind of abuse has to be made, otherwise things will become very, very unwieldy. All right. Lastly, let us look at a non-example. So consider the set of all the integers. The set of all the integers is defined as this set. And this triple, the usual addition and the usual multiplication that we perform on integers, this is not a field. Why is that? Because you take this number 3. 3 does not have a multiplicative inverse. Which means what? If you recall the definition of a multiplicative inverse, it means that there does not exist. That is, there does not exist some beta in Z such that 3 times beta is the multiplicative identity of Z. But what is the multiplicative identity of Z? 1. The usual, the unit. And clearly there is no such integer beta, right? Because the only beta that can satisfy this is the rational number 1 by 3, and that is not an integer. So integers, meaning this triple, this is not a field. Okay, so I don't think there is anything more here. Before I leave, I want to mention that all of this must feel very, very abstract and useless, but this is just the first lecture, and the reason or the usefulness of this cannot be elaborated in just a matter of 20 minutes. So I would suggest you hang on, and very soon we will see very, very concrete applications of what we are doing. Linear algebra is a very fundamental, beautiful, and foundational subject in higher mathematics, which cannot be avoided by any student. So let that be the motivation to read it at this moment. Alright, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.